Hello everyone, welcome to the course on basic electronics. Here we are discussing about module 1, semiconductor diode and its applications. So in this session we will discuss about diode applications like what is a rectifier and the different types of rectifiers like half wave rectifier, under full wave rectifier, center tapped rectifier and a bridge rectifier, full wave rectifier power supply, capacitor filter circuit, RC pi filter, all these things. Half wave rectification. So one of the most important applications of diodes is rectification. Conversion of a sinusoidal AC waveform into single polarity half cycles. Rectification may be performed by half wave or full wave rectifier circuits. A DC power supply converts a sinusoidal AC supply to DC by rectification and filtering. The filtering process normally involves the use of a large reservoir capacitor which charges to the peak input voltage level to produce the DC output. The capacitor partially discharges between peaks of the rectified waveform, and this results in a ripple voltage of the output. The ripple can be reduced by the use of RC or LC filters. Power supplies are specified according to the DC output voltage, load current, and ripple voltage. Power supply performance is defined in terms of the output voltage, stability when the input voltage or the load current changes. Other important diode applications includes clipping, clamping, DC voltage multiplication and logic circuits. Diode clipping circuits are used for clipping off an unwanted portion of a waveform. Clamping circuits change the DC level of voltage level of a waveform without affecting the wave shape. DC voltage multipliers are applied to change the level of a DC voltage source to a desired higher level. Logic circuits produce a high or low output voltage depending on the output voltage levels at several input terminals. Coming to the half wave rectification, first we will discuss about positive half wave rectifier. A diode positive half wave rectifier circuit is as shown here. An alternating input voltage is applied via a transformer T1 to a single diode connected in series with the load resistor RL. The transformer is normally necessary to DC isolate the rectifier circuit from the AC supply. Diode is forward biased during the positive half cycles of the input waveform and reverse biased during the negative half cycles. Substantial current flows through RL only during the positive half cycles of the input. For the duration of the negative half cycles, the diode behaves almost as an open switch. The output voltage waveform developed across RL is a series of positive half cycles of alternating voltage with intervening very small negative voltage levels produced by the diode reverse saturation current. When the diode is forward biased, the voltage drop across it is Vf and the output voltage is input voltage, that is minus Vf. So the peak output voltage is given as Vpo is equal to Vpi minus Vf. So that if we note or if we assume Vpi is equal to 1.414 times of input voltage. So here Vi is the RMS level of the sinusoidal input voltage to the rectifier circuit from the transformer output. The diode peak forward current is Ip is equal to Vpo by RL. During the negative half cycle of the input, the reverse biased diode offers a very high resistance So there is only a very small reverse current IR giving an output voltage minus V naught is equal to minus IR into RL. While the diode is reverse biased, the peak voltage of the negative half cycle of the input is applied to its terminals. Thus, the peak reverse voltage or peak inverse voltage applied to the diode is VR is equal to PIV is equal to VPI. The average and RMS values of the half wave rectified waveform can be determined as V naught average is equal to 0.318 VPO and V naught RMS is equal to 0.5 VPO. However, most rectifier circuits use a reservoir capacitor at the output terminals to smooth the rectified voltage wave into direct voltage. So it becomes very important to note that the presence of the capacitor changes the output waveform and that it substantially affects the load current and voltage and the diode current and voltage. So during negative half wave rectifier, so the effect of reversing the diode polarity in the circuit of figure, the negative half cycle of the AC input waveform is passed to the load resistor. Consequently, the peak output voltage and current are negative quantities. Figure shows a positive half wave rectifier circuit with the positive output terminal grounded. This is possible because the AC input to the rectifier circuit is normally derived from the secondary of a transformer. Either of the two output terminals may be grounded so long as there is no other grounded point in the circuit. Now, when the transformer output waveform is at its peak positive level, the load of waveform is actually a peak negative quantity. Because output terminal B is negative with respect to the grounded terminal A. The diode is reverse biased during the negative half cycle of the transformer output, and so the load voltage is zero. Thus, the negative half cycle, negative half wave rectified waveform can be generated by simply by grounding the positive output terminal of a positive rectifier circuit. It is important to note that one of the rectifier circuit output terminals may be grounded only when the transformer is present to provide complete DC isolation from the AC supply. If a variable transformer is used without a power supply transformer, a 1:1 isolation transformer must be substituted for the power supply transformer to provide the required DC isolation. So coming to the full wave rectifier, it's a two diode full wave rectifier. The full wave rectifier circuit uses two diodes and its input voltage is supplied from a transformer that is T1 with a center tapped secondary winding. The circuit is essentially a combination of two half wave rectifier circuits, each supplied from one half of the transformer secondary. When the transformer output voltage is positive at the top, so in figure A, anode of the diode of D1 is positive and the center tap of the transformer is connected to the cathode of diode D1. by RL. So D1 is forward biased and load current IL flows from top of the transformer secondary through D1 load current IL uh, through RL from top to bottom and back to the transformer center tap. During this time, the polarity of the voltage from the bottom half of the transformer secondary causes diode D2 to be reverse biased. For the duration of the negative half cycle of the transformer output, the polarity of the transformer secondary voltage causes D1 to be reverse biased and D2 to be forward biased. IL flows from the bottom terminal of the transformer secondary through diode D2 through RL from top to bottom and back to the transformer center tap. The output waveform is the combination of the two half cycles, that is a continuous series of positive half cycles of sinusoidal waveform. So this is positive full wave rectification, and if the polarity of the diodes is reversed, the output waveform is a series of sinusoidal negative half cycles, negative full wave, negative full wave rectification. The center tap of the transformer is normally grounded, and so the only way to obtain a negative output from this type of circuit is to reverse the diode polarity. Next is full wave bridge rectifier. Center tapped transformer used in the previous circuit is usually more expensive and requires more space than additional diodes. So a bridge rectifier is the circuit most frequently used for full wave rectification. The bridge rectifier circuit is seen to consist of four diodes connected with their arrowhead symbols and all pointing towards the positive output terminal of the circuit. Diodes D1 and D2 are series connected, as are D3 and D4. The AC input terminals are the junction of D1 and D2 and the junction of D3 and D4. The positive output terminal is at the cathodes of D1 and D3, and negative output is at the anodes of D2 and D4. During the positive during the positive half cycle of input voltage, diodes D1 and D4 are in series with RL. The load current IL flows from the positive input terminal through D1 to RL and then through RL and D4, so back to the negative input terminal. The direction of the load current through RL is from top to bottom. During this time, the positive input terminal is applied to the cathode of D2 and the negative output is at the D2 anode. So D2 is reverse biased during the positive half cycle of the input. Similarly, D3 has the negative input at its anode and the positive output at its cathode during the positive input half cycle, causing D3 to be reverse biased. So figure C and D shows that diodes D2 and D3 are forward biased during the negative half cycle of the input waveform, while D1 and D4 are reverse biased. Although the input terminal polarity is reversed, IL again flows through RL from top to bottom via D3 and D2. It is seen that during both half cycles of the input, the output terminal polarity is always positive at the top of RL and negative at the bottom. Both positive and negative half cycles of the input are passed to the output. The negative half cycles are inverted so that the output is a continuous series of positive half cycles of sinusoidal voltages. A full wave bridge rectifier circuit always requires that the input be derived from a transformer that provides DC isolation from the supply. The circuit will not function correctly if one of its input terminals is grounded. However, given the required DC isolation between supply and output, either output terminal may be grounded to provide a positive or negative output voltage. The bridge rectifier has two forward biased diodes in series with the supply voltage and the load. Because each diode has a forward voltage drop, Vf, the peak output voltage, and it is Vpi minus 2 Vf. So the average and RMS values of the full wave rectified waveform is V naught average is equal to 0.637 VPO and V naught RMS is equal to 0.707 VPO. So once again, it should be noted that most rectifier circuits use a reservoir capacitor to smooth the rectified voltage wave into direct voltage, and the presence of the capacitor changes the output waveform and substantially affects the load current and voltage and the diode current and voltage. So these are the two circuits which shows the effect of negative half cycle of input effect and also effect of positive half cycle of input, where in positive half cycle D1 and D4 are forward biased, in negative half cycle D3 and D2 are forward biased. There are two more ways of showing bridge rectifier circuits. These are exactly the same as the circuit in the previous circuit. So these are the circuits for full wave rectifier. Thank you.